So now that we have explored differentiation with vector-valued functions, we are officially ready to begin our exploration of integration with vector-valued functions. And just like our real-valued functions, vector-valued functions have both indefinite integrals and definite integrals. So the first case that we are going to explore is the indefinite integral of a vector-valued function. So here we go. If vector r of t, defined by f of t I hat plus g of t j hat plus h of t k hat, where f, g, and h are continuous and differentiable functions of our arbitrary parameter t, then its antiderivative is defined as follows. So we have the integral of our vector-valued function r of t dt is equal to the integral of this vector-valued function. So we have, putting this into its component form, the integral of the vector f of t, g of t, h of t, dt. And now, just like with evaluating the limit or finding the domain of a vector-valued function, it's oftentimes going to be a little easier for us if we think about this antiderivative component by component. So we can write this out as the sum of the separable components. So we have the integral of f of t dt I hat plus the integral of g of t dt multiplied by j hat plus the integral of h of t dt multiplied by k hat. So this, once we're done our integration, leaves us with the general solution, or the antiderivative, capital vector R of t, and this is going to be equal to the antiderivative of f I hat plus the antiderivative of g j hat plus the antiderivative of h k hat. And now we have plus c. And this c here is a vector. So we'll just keep in mind, we can say, well, let's write this in its alternative form first. We can, of course, also write this as the component form. So we have the antiderivative of f, the antiderivative of g, the antiderivative of h, plus your vector c. So this is such that c is a vector, analogous to the constant that we add to an antiderivative of a scalar valued function. Now, I also want you to note that while this is our general solution, just like with real valued functions, we can narrow the family of antiderivatives for a vector valued function down to a single antiderivative by imposing an initial condition on our vector valued function. And we'll explore this in more detail with the examples. But first, we now need to go ahead and establish the definition of a definite integral of a vector valued function. So let's go ahead and take a look. So here we go. The definition for the definite integral of a vector valued function. So again, if vector r of t, defined by the components f of t I hat plus g of t j hat plus h of t k hat, where f, g, and h are all continuous functions on a closed interval such that t is greater than or equal to a, less than or equal to b, then its definite integral over this closed interval from a to b is defined as follows. So here we have the definite integral, so we're incorporating these bounds. We have the integral from a to b of the vector valued function r of t dt. And again, we can think about this as the integral, the definite integral from a to b of that vector valued function, f of t, g of t, h of t, dt. And now, just like with the indefinite integral, it's oftentimes going to be easier if we think about this integration component by component. So we can say this is the definite integral from a to b of f of t dt I hat plus the definite integral from a to b of g of t dt, j hat, plus the definite integral from a to b of the h of t component dt, k hat. And so after integration, we are left with that antiderivative vector, capital R of t, but this time we are evaluating this from a to b. So this is going to leave us with the following. We have the antiderivative of f times I hat plus the antiderivative of g, j hat, plus the antiderivative of h, k hat. And we evaluate this from a to b. So we can even take this one step further and think about this as the difference of these two vectors. So we have the antiderivative vector evaluated at b. So we have f of b, g of b, h of b, minus the antiderivative vector evaluated at a. So we have f of a, g of a, h of a, and just a little bit more room. So we can see here in looking at this definition that we're going to be left with a vector. So these two definitions are analogous to the definitions that we know for definite integrals and indefinite integrals of real valued functions. And these integration techniques that we know and love from our real valued functions are also going to hold true here with vector valued functions. So get excited. Let's go ahead now and look at some examples.